Okay. Hi, everyone. My name is Matteo Tesio. I'm a research student of the Politecnico di Torino. And today I'm here with my reference professor, Stefano Invernizzi. Okay. This is the index. We will follow this point for the presentation today. So let's start with some information regarding the location of this artifact. The building is located in a region in the north of Italy, more precisely in Piedmont. This area is located between Milan and Turin, two of the main Italian industrial poles since the first decades of 20th century. This region was very important area for the Italian economic development, as many important industries developed in this zone. The structure belongs to the municipality of Casale Monferrato. More precisely, is located in its industrial area, on the south of the city, near the railway station, as you can see from the area zoom. The structure is commonly called paraboloid. It was built in the beginning of the 20s from the Italcementi company of Bergamo as a warehouse storage for industrial material, clinker. It is located in the southern part of the city of Casale. After the end of the activity of the Italcementi, during the following years, most of the structure were demolished, with the exception of the paraboloid, which was used as a timber warehouse from the 50s onwards. It's unclear if the central pillar and the internal beam were added in this period, or if the chain were pre-existing. Their purpose was to counteract the internal tooth of the arc and act as a support base for a raised storage level added on the structure. Since the 80s, the structure has remained in use and in a very poor state of conservation. The paraboloid is considered as a reference icon of the industrial past of Casale, being in fact one of the first buildings in reinforced concrete made with this particular shape. On the side, there are some scans. These two scans are the only one technical document that we have been found about the paraboloid of Casale. They have been recovered from the book Reinforced Concrete in Civil and Industrial Building by Luigi Santarella. Being a structure of historical and artistic interest protected by the Cultural Heritage and Landscape Code, in the last decade, it was being the object of analysis aimed at the architectural conservation of the asset and the requalification of the neighbor. The survey was performed using high-resolution terrestrial laser scanning technology, LIDAR, mixed with aerial survey by the Laboratory of Geomatic for Cultural Heritage of the Department of Architecture and Design of the Politecnico di Torino. The cloud of points were processed with appropriate software, allowing to extract the geometric profile of each element of the structure and return them in architectural design format, 2D, section, and elevation. Here you can see some of these 2D drawings. We have used this drawing for extract the coordinate used in the Diana model. Before that, we have cataloging of each element of the structure, and we have imposed a reference system for extrapolated the coordinate used in Diana. Here you can see some example of geometric profile coordinated extracted from 2D representation of arc and buttress element. So now we'll start the first video. I will show you some of the main topics for model the paraboloid. Let's start by creating a new project file and setting the default mesh order to quadratic. The arc coordinates extracted from the model are entered using the add-point command and selecting multiple input options. The input can be easily done by using copy and paste command from Excel file, as you can see in the video. Then we have defined two curves passing through the imported point with the add_cure command. These two curves will represent our parabolic arc. For the top part of the structure, we have used the line command between the endpoint of the two curves. After having defined the basic geometry of the arc, it was extruded in Y direction to create the cover vault. After that, the initially imported construction point can be deleted because they will no longer use in the model. Due to the large number of elements inserted in the model, the shape set which contain them has been renamed with the code of the corresponding element. To be sure that the beam element representing the arc actually lies on the vault, the select geometry edge function has been used to select the outer line of the vault. Then the line constituting the arc has been obtained using the extract command. We now proceed to insert the second warp beams of the vault. Then we import the coordinates of the beam obtained from the architectural plan of the model using the same procedure seen before for the construction point of the arc. After having imported them, the point has been extruded in X direction in order to create the line representing the joints. Then the shape reaction command in the positive vertical direction was used unchecking the tick on imprint. This command allows us to project the line representing the joint exactly on the vault surface. Be sure that the direction is vertical positive. Then we proceed to positioning of the main arches along the vault with the array copy command. Once all of this has been done, to complete the simplified construction of the paraboloid cover, we need to insert the closing wall of the vault in the east-west direction. Here you can see all the numerical input of the array copy command. So now let's add a polygon sheet using the right command. We have select the rectangle method, positioned at the base of the arch with YZ reference plane and with dimension such as to cover the entire opening of the vault. Subsequently, using the subtract shape command, we will subtract the three surfaces that represent the vault of the paraboloid from the newly created surface, and then we eliminate the exact part using the face selection function. Now we have the main part of the vault modeled. We will insert the pillar that supports it. The pillar will be created with the add polygon command using the coordinate method. So let's take the coordinate from the pillar from Excel file and paste them into Diana. After its creation, the selected pillar, we select the pillar with the mirror command, and after assigning the axis on the base of the pillar along a Y direction, we get the two supporting pillar of each arc. Then, using the move shape command, we will place the pillar in the support point of the arc. After positioning the first pair of pillar, we can use the copy array command to complete the positioning of the other pillar and the insertion of the closing wall on the west side of the paraboloid. This projection procedure guarantees that the correct mesh connection between beams and shell element will be obtained. The remaining part of the structure have been modeled using the same command previously shown, and using the coordinate extract from the table and the basis for their positioning. The construction of the model was a very long process that, for time constraint, I cannot show you entirely today. Here you can see the result of the element modeled. Another fundamental step for the calibration of the model is the assessment of the mechanical property of the existing building. The preliminary visual investigation of the site reported a general degradation of the material of the structure and extensive corrosion of the reinforcement, often accompanied by the spalling of concrete. The main cause of the structural damage is to be attributed to aging. In addition, the poor condition on the roof, ceiling, and the lack of maintenance of the building has involved an infiltration of rainwater, which is extremely harmful with respect to reinforcement corrosion. Given the poor state of conservation of the structure, a series of diagnostic tests were carried out on the main structural element in order to assess the mechanical properties of the various elements of the building. The tests carried out were coring, pull-out, ultrasonic, and pachymetric tests. The coring test consists in the extraction of a specimen from the structural element, which will then be subjected to mechanical tests in order to investigate the properties of the element from which it has been extracted. They have been extracted on the main structural element in order to have a picture uniformly distributed and representative of the entire structure. The resulting quality of the concrete was practically inhomogeneous. You can see here a chemical test to assess the concrete carbonation dip. Okay, now let's talk about pull-out test. This type of test consists of extracting from the concrete surface a steel insert of standard dimension by means of an extractor unit resting on the surface of the structural element. The test can be considered semi-destructive, as it causes slight superficial damage to the structure. This method allows to extend the control of the concrete resistance in singular point of the reinforced concrete structure. Ultrasonic test. The theoretical principle of this method is based on propagation of longitudinal elastic wave in a medium. Considering that the speed of propagation in a homogeneous medium is a function of its physical properties. It is therefore possible to correlate the speed of propagation to the elasticity of the concrete. On the basis of the speed obtained, an estimate of the elastic modulus of each element investigated has been obtained. The pachymetric tests have been used to verify in a non-destructive manner the presence of any reinforcement in the structural element of the building. Given the lack of original design drawing, the tests were useful to determine the present direction and estimate the thickness of the iron cover of the various elements under investigation. The processing of the data obtained from the mechanical test provided the mechanical properties to be assigned to the element, accounting for the current degradation condition. Now, I will show you another small video where we apply the mechanical properties to the Diana model. Let's start with the support. The support will be placed on the ground support line of the pillars. So we add a new set of support. The target type in this case will be edge. we select the line that we want to bind, and we go to block all the translation and rotation. After attach the support, we can see that the constraints are displayed at the ground support of the pillar. The visualization can be activated and deactivated by checking the appropriate box. After defining the constraint of the structure, we will now create the material of the element that composes it. As a class for the material has been used concrete and masonry, and as a material model has been selected the Maekawa-Fukura model. This type of material requires mass density, tensile strength, and uniaxial compressive strength data as input. The values used are those obtained from the mechanical test shown before. Therefore, we proceed by creating material that serve for the definition of the model elements. Let's create the second material used for the pillar. We have used a different number for each element. Here the material used for the secondary beam. Okay, after having created them, we then proceed to assign the properties to the element using the property assignment command. For the line element, we select the element class 3 beams 3D. As material, the previously created material is assigned, which corresponds to the element, and as geometry, we will define the property of the geometry of the element according to what obtained from the 2D drawings. We now move on the assignment of the properties of the vault. In this case, as a class, we use regular curved shell, and after assigning the material, we will create the geometry. Also, for this element, after setting the thickness, we assign an eccentricity, because we want the vault to be in line with the upper part of the arc. This step is crucial in order to respect the correct geometry arrangements of the real structure. So let's proceed by repeating the same step for all the elements of the structure. for beam type element, we input height and width parameter. The next step consists on the assignment of the load to the structure. We go to the load tab and use the command define global load to create the self-weight load. We create the load case and we select the load type. Finally, the last part we still have to define are the reinforcement. For their creation, then we will duplicate the line that represent the beam element, moving them along the z-axis to represent the upper and the lower warp of the iron in the element. The step is then repeated for all the beam elements that will then be collected in a single shape set. Now we duplicate the secondary order beam for the reinforcement creation. And we move them in the right shape set. To assign the right characteristic to this line element, we will use the reinforcement properties command. We will select all the elements in the set and go to create the new material to assign. The class in this case, it will be reinforcement, and as a material model, von Mises plasticity has been used. We then proceed by entering the data required by the material and move on to the geometric properties of the reinforcement by entering the total cross-section area of the bar. As far as the volt is concerned, a reinforcement grid has been assigned by duplicating the representative element of the volt and assigning them the reinforcement properties. Then we define the material as it has been done for the iron beam element. As geometry, in this case, we are asked to enter the var diameter and spacing between bar in X and Y direction. Here we use the data collected from the phacometric test for the spacing between bars. We go then to verify in the model display that the reinforcement elements have been correctly inserted. They are represented in blue color. The last thing we have to define are the mesh generation properties. So let's select the wall structure. Let's open the mesh properties panel. Verify that the target is on shape and the seeding method on element division. We assign the desired mesh size and apply the properties. Okay, now we can generate the mesh model using the generate mesh command. Here you can see some screenshot of the complete model that we have used for the Diana calculation. The screenshots are taken using the 3D preview of the mesh selection in Diana. Okay. The following analyses were performed on the model: structural linear static, structural eigenvalue, structural direct response, response spectrum, and structural nonlinear. According to the Italian standard, we considered gravity load, snow load, and wide action for the structural linear static analysis, together with the seismic load to assist the stability of the structure element. Here you can see some screen of the combination between wind and snow. According to the nodal displacement, the resultant contour plot, we can observe that the upper and the lateral canopy are generally in critical condition. We have plot using Diana representative diagrams of moment and compression stresses in arched beams of the paraboloid. Note that the bending moment discontinuity in correspondence of the connection with the upper and the lateral canopies. We have performed an eigenvalue analysis. We perform a free vibration analysis in order to calculate the first 100 modes of the model. Here you can see two little clips created using the Diana corresponding function. The modal analysis allowed for the selection of predominant modes, including those with tighter participant mass. Here you can see the mode 2, the mode 5 with predominant vertical action, and the mode 29 that have action in all the structure local axes. Okay, for the structural direct response analysis, we have applied a base excitation load to Diana model. And we have plotted the two graphs below that show the horizontal displacement of particular point of the structure. The peak corresponds to the eigenfrequency previously calculated. Okay. The results were compared with those obtained from the dynamical test carried out on the structure. 20 accelerometers have been positioned inside the structure, following different schemes in order to obtain the data from natural excitation and excitation caused by impulsive force. Here you can see the first setup of accelerometer use. Using a SSI algorithm, dynamic identification of the structure in terms of frequencies, shape, and modal damping was performed in the time domain, using directly collect data. The comparison between the results obtained from the acquisition on the structure and those obtained from the model made it possible to verify its actual calibration. Here you can see some graphs of the modal, shape, frequency, and damping identified for the model before and after the calibration. In order to have a complete picture of the structural element and following the indication prescribed by the NTC 2080 regulation, analysis has been carried out to simulate the paraboloid response in case of earthquake. Before running the analysis, a typical earthquake spectrum is applied to the load amplification factor for the base excitation load. In the first stage, the elastic spectra were considered Q factor equal 1. Here we can see some line diagram extract from Diana analysis. This is the cross-section forces, and this is the cross-section moment diagram. The analysis have enlightened a vulnerability of the structure concerning seismic action. In fact, the shell structure involves a multitude of vibration modes, some of which are significantly amplified by the earthquake spectrum. The structural design checks were carried out combining the effect of seismic action in different directions with the static effect at the ultimate state condition. Appropriate reinforcement section and strength are considered to account for carbonation and corrosion. The internal chain are among the most critical structural elements. The collapse will take place due to shear. The chain collapse or removal promote the shear collapse of the batteries. Finally, in order to obtain an accurate and realistic prediction of a structural seismic response, it is necessary to have an analysis tool to capture nonlinear behavior and its evolution over time. To perform this type of analysis, a pushover load must be applied to the calculation model. The pushover will be increased incrementally with a series of load steps. Diana's output function allows us in order to see the part of the structure that are with crack openings. The nodal results of the analysis were used to create a graph with the total based shear force versus displacement in y direction in the middle part of the vault. The pushover curve can be used to obtain an estimate of the reduction level of the seismic forces. The numerical simulation provides that the level of safety among the different structural elements is quite variable. The most critical elements are the internal chains, followed by the batteries and the longitudinal beam at the top of the batteries. In addition, the failure mechanism of such element is due to the reaching of the limit shear capacity before a brittle mechanism. The secondary longitudinal beams and the vault shear are in quite poor condition due to the extensive carbonation of the concrete and the corrosion of the limited amount of present reinforcement. The nonlinear analysis conduct considering both mechanical and geometrical nonlinearities showed that the instability is not likely to affect the structure. In view of a possible intervention, this must be carried out in conformity with the national standard for cultural heritage. The first structural elements to be retrofitted should be the internal chains. Subsequently, and depending on the possible change of use of the structure, the retrofitting should be directed to the buttress and main arches. Finally, it is suggested that secondary beam and the thin vault should be completely replaced. Thank you for your attention, and that's all. Now